When we left off, we were talking about the complexity of molecular orbitals. But we made the bold statement that we're really only interested in the highest energy pair of electrons in any nucleophile. And we're only interested in the lowest energy orbital in any electrophile. And we refer to these orbitals as the frontier orbitals. And frontier orbitals come in 6 types. There are 3 types of filled orbitals, and there are 3 types of unfilled orbitals. Every single arrow that we push in this class is going to start from one of these 3 classes of filled frontier orbitals. And every single arrow will end, every single curved arrow will end at one of these 3 types of unfilled orbitals. So these are the frontier, these are the 6 canonical types of frontier molecular orbitals. And it's powerful for you to memorize the energies of these orbitals, because if all else is equal, then what you want to do is you want to start your arrows from the most reactive pair of electrons. So that would be lone pairs, non-bonding lone pairs. Start your arrow with a lone pair. 95% of the time your arrows will start with lone pairs. If you have no lone pairs in your molecule, well, start thinking about pi bonds as the place to start your arrow. And if you have no pi bonds and no lone pairs, you're kind of down to sigma bonds. Your arrow is probably going to start with some sort of a sigma bond. And likewise, when we make our arrows end, when we attack something in order to form a new bond, if you have an empty p orbital, like a carbocation in your molecule, attack there first. You probably already knew that carbocations are reactive. Well, that's because they're the lowest energy class of unfilled molecular orbitals. If you have no carbocations or empty p orbitals in your molecule, maybe you can start thinking about attacking double bonds, right? That's pretty standard. Usually carbon-oxygen double bonds, carbonyl groups are one of the main types. And then finally, if you have no carbocations and no double bonds in your molecule, then maybe you can start to think about doing SN2 type reactions in order to break bonds. And that's when that becomes reasonable. So memorize the energies of these frontier orbitals, and they'll provide you with a guide on how to start your arrow pushing steps. Let's go ahead and take a further example with that. Let's take a transformation that I don't think you've seen before. I'm not even sure if this is real, but it's a case where you can anticipate what might happen here. I'm showing you the product, which gives you a big advantage in this process. So if you look very carefully, what has happened is we now have an H atom that wasn't there before. So a hydrido group has been transferred. Now I'm going to go back to the starting materials. Where is that hydrido group? Where is that hydrogen atom? There it is. It's right there next to the oxygen. So what happened in this reaction? What happened is that this hydrido group has come over here and attacked a double bond. It attacked pi star. I'm going to keep pushing the arrows here, but at the end of the day, we attacked a pi star system, and we used a sigma bond to attack that. So we used this sigma bonding orbital down here to attack pi star. Now, didn't we say that lone pairs are the most reactive parts of molecules? How come I didn't start with that sigma bond? Well, that's what explains why is that CH bond so reactive. That CH bond is so reactive because these lone pairs on oxygen were donating into the antibonding orbital for that sigma star CH. They weaken the CH bond, they make the CH bond more nucleophilic, and so the interaction that you're getting is a sigma bonding orbital interacting with this pi star orbital in the electrophile. But the reason why that sigma bond is so nucleophilic is because of that oxygen lone pair. And I'm not going to go into it right now, but that tin carbon bond obviously has a big effect on the reactivity. But let's set that aside for just a moment. So we need to go into a little bit more detail, go a little deeper on these types of interactions between orbitals, between a filled orbital and an unfilled orbital. And I'll show you a tool that you can use to analyze those interactions when you want to make simple comparisons. Simple comparisons. And so the tool that I'm going to introduce you to is called a molecular orbital interaction diagram. And these diagrams, these graphical depictions, are based on a simple equation. And this simple equation is that the amount of energy that you get out, the amount of stabilization you get out of a pair of electrons, usually the whole molecule, not always, or the stabilization that you get to a transition state, right? Lowering energies of transition states accelerates chemical reactions. The amount of energy that you get, the energy lowering, is proportional to the overlap between the two orbitals. There's a filled orbital adding to an unfilled orbital, and the better the overlap, well, the more energy you're going to get out of that process. The other two variables that are in there is the energy of the nucleophilic orbital. You want that to be high in energy. And then you also want to pay attention to the energy of the LUMO, the unfilled orbital. So sometimes we would refer to these as HOMO and LUMO, but those are the three variables that matter. How much overlap in space you're getting when the two orbitals come close together, the energy of the nucleophilic orbital, and the energy of the empty orbital that you're putting electrons into. And we often depict this graphically like this. So we draw out some sort of a filled orbital, and we draw an energy line on this arbitrary axis. So we've got this vertical axis here that's in electron volts. Who cares? You know, notice we're not trying to plot actual numbers here because you don't ever know the numbers in electron volts for these. Now, what is true is that the unfilled orbital will always be higher in energy. So that would be over here. That would be this unfilled orbital, unfilled. It'll always be higher in energy. And the thing that we are interested in identifying here, the thing that matters the most, is this denominator. And that is the gap. We're interested in the gap, the energy gap. Here, this gap between the filled orbital and the unfilled orbital. And in this case that I've drawn for you here, this hypothetical case, I didn't draw a reaction, this gap looks small. And so what happens if the denominator in our simple equation here is small? If the denominator is small, then we will get a lot of interaction energy out. We're either going to lower the transition state of some reaction by a lot, or we're going to get a lot of resonance donation. Those are the two typical scenarios where we're interested in this. And so let's try to depict that graphically. If we get a lot of interaction energy out, here's the interaction energy. If the gap is small, we're going to get big interaction energy, big orbital interaction energy out. And importantly, the new orbital that we make when we add filled to unfilled and make a new bond, we'll get this big interaction energy out. We'll also generate an antibonding orbital at the same time. And that antibonding orbital will be raised in energy by exactly that same amount. So interaction energy, it's that same interaction energy is how much you'll raise the energy of that new antibonding orbital. So you mix two orbitals together, you'll get two orbitals out. You get a bonding orbital and an antibonding type orbital. Okay, what happens if I have a nucleophile that is not very reactive? So let's take this case over here where I'm starting to draw another diagram and I have a low energy. See how much lower that is than my case over here? What happens if my filled orbital is low in energy? Not very nucleophilic. Low in energy, a pair of electrons that's low in energy is not nucleophilic. And what happens if I'm trying to add that to an orbital that's high in energy? What if the empty orbital is really hard to add to? What will happen in that case is I'm going to end up with this big gap. The energy difference, if I plug it into my equation, I'm going to have a big gap right here. This difference right here in energies between these, that gap, this gap right here is big. And that means the denominator to that equation is going to be big. And if the denominator in this equation is big, that means you get very little orbital interaction energy out. So I'm going to get very little orbital interaction energy out of this is what I would predict. Right? I'm just qualitatively trying to compare what happens if I take lame nucleophiles and lame electrophiles and I interact them together. Well, I'll get this situation where, so let me go ahead and draw these interaction lines. You always get a parallelogram. In these, it'll be a perfect parallelogram. So that would be the implication. You would not get a big interaction. You would not have a very low energy transition state. You wouldn't get a lot of transition state energy lowering. You wouldn't get a lot of resonance if we were trying to depict a diagram for resonance. You want a small gap between the filled orbital, the HOMO, and the unfilled orbital, the LUMO. That's what leads to productive interactions. So we always want to use these diagrams to compare two situations where we've changed one and only one variable. If you're changing multiple things, you're not going to be able to get any information out of these diagrams. So let's go ahead and take a look at how to use these diagrams to analyze situations where we've changed one and only one thing, where we've made just a slight perturbation, and we want to understand what's the effect of that perturbation. So here's an example where I'm taking two different nucleophiles and I'm attacking the same electrophile. So what happens if I take hydroxide versus fluoride attacking a carbonyl group? So what are we adding to? And well, it's the electrophile in both cases is the same. In both cases, we're adding to a pi star orbital, specifically pi star CO. Same on the other side with fluoride, we're adding to a pi star orbital, CO, pi star. And the only thing that's different is what kind of lone pair we're adding. So here we're starting off with a non-bonding lone pair on oxygen with a minus, and here we're starting with a non-bonding lone pair on fluoride with a minus. And I hope you know, without any diagrams, that fluoride is a worse nucleophile. Fluoride is more electronegative, it should be less nucleophilic. I hope you know that the fluoride loves having its electrons, doesn't want to share anything. But let's see how we can see the same picture at a slightly deeper level using a molecular orbital interaction diagram. And I'm going to start with the oxygen, the hydroxide diagram. So here I've indicated that, just qualitatively, I've indicated that the hydroxide, the lone pairs on hydroxide are high in energy. They're very nucleophilic. And pi star I've got over here. So the gap over here is going to be reasonably small. I'm going to get a strong interaction if I add, right? This is a small gap. I'm going to get a small gap there between the filled orbital for the hydroxide anion and the empty orbital of the carbonyl. And because that gap is small, I'm going to get a big interaction energy out. You'll get a big interaction energy out, and you'll get the same interaction energy. It won't, in this case, it doesn't really matter, but make sure that you raise the new sigma star orbital the same amount in energy as IE. Now, what happens to this diagram if I switch from an O minus to an F minus? Well, you already know that fluoride, lone pairs on fluoride are less reactive. You should know that. And so it shouldn't be surprising to you that I'm drawing the energy for this fluoride-filled orbital over here lower in energy than I drew the oxygen lone pair, the non-bonding lone pair for oxygen. So because that's lower in energy, look, the CO here is going to be at exactly the same level. I didn't change that. But when I draw a diagram for this nitrogen-fluorine bond, this gap is going to end up being bigger. The gap is bigger. This is a big gap now. Or I should say bigger gap. I'll just say big gap. But the gap is noticeably bigger. And that means that the interaction energy that I get out of here is going to be smaller. Now, you don't know exactly how much smaller that is. You can't predict that. And I'm going to generate a new orbital when I make this bond between carbon and fluorine, an FC bond, or you could say CF bond. And I'm also going to, at the same time, generate a new antibonding orbital. And if this went down by this much energy, then the new antibonding orbital is going to be up by the same amount of energy. And I'll end up with this diagram, this MO diagram, that should tell me and that new MO diagram should tell me that I'm going to get less interaction energy out. It's just telling you that it's less favorable, that because you get less interaction energy out in this case, because the gap is bigger, the amount of interaction energy you get out is smaller. So the transition state for fluoride addition to carbonyl won't be lowered as much as you lower the energy of a transition state for hydroxide. It's just not as favorable to add fluoride in, and you can see that from the interaction energy in this diagram. Now, this wasn't very useful because you already know the answer here without drawing any diagrams. We're just trying to take a simple case. Let's go ahead and take another step to see how we can see another comparison. This time, not two molecules reacting with each other, but a case of resonance versus no resonance. So let's take the case where I've got two different groups, and it's not so obvious here, but I've got two different groups here, or two different situations. One where I have a lone pair donating into a carbonyl pi star. Let's draw that. So here I've got a non-bonding lone pair on oxygen, and I've got a pi star over here, CO. And how would we compare the reactivity of this carboxylic acid carbonyl to just a simple aldehyde CO? Which of those is more reactive? Right? How could we use an orbital diagram to analyze that interaction? And we're not seeing every aspect of reactivity. There's electronegativity or polarity effects that we're not seeing. But if we drew an interaction diagram for this, what we would say is, wow, oxygen lone pairs are or reasonably nucleophilic, there's going to be some sort of gap. We're just being qualitative here. There's a gap here between the filled orbital and the unfilled orbital. And because of that gap, we get new orbitals out that are lower in energy and an antibonding orbital that's higher in energy. So that's resonance, right? You can use these diagrams when two molecules are colliding and overlapping, and orbitals overlap in space, or when the atoms are right next to each other and there's resonance and there's overlap of orbitals in space. So I'll get two new orbitals out. I'll get a pi-like orbital out of this, pi OCO, and then I'll get some new pi star orbital, OCO, and it will be raised in energy by the same amount that I lowered my new orbital in energy. That's that interaction energy. And let me go ahead and draw those dashed lines here. We it helps me to see that there's a parallelogram there. Now, what are the two orbitals I'm trying to compare? So if I come in separately now and I try to add a different nucleophile, an amine, an alkylithium, some sort of other nucleophile, cyanide, anion, to these two carbonyl groups, which carbonyl group would be more reactive? Well, what I want to do is I want to look at which pi star system is lower in energy. The pi star system that has resonance or the pi star system that had no resonance, just an aldehyde. And H has no extra orbitals that can donate into that CO bond. So that's pretty easy. I can see that the CO that has no resonance is lower in energy than the pi star that has resonance. So that tells me that because this is lower in energy, because this orbital is lower in energy than when I have resonance, it's easier to add to carbonyls that don't have resonance. That's easier. So easier to add when there's no resonance interaction. This is why it's harder to add to ester carbonyls than aldehyde carbonyls. This is why it's harder to add to amide carbonyls than aldehyde or ketone carbonyls. That resonance of the lone pair creates a new orbital that's harder to add to, a new pi star type orbital. So again, we're comparing two situations with and without resonance here, and in this case, you can see it all in one diagram. All right, let's take one last case where we're just kind of practicing to see how you would use these molecular orbital interaction diagrams. I've got two different carbonyls here. I've got an amide carbonyl and a carboxylic acid carbonyl. I'm just asking a similar question that I did before. Which is easier to add to? An ester or carboxylic acid carbonyl or an amide carbonyl? It's the same pi star in this case, right? I can't change all kinds of things at once. So it's pi star CO and it's pi star CO. And what I'm changing here is the nucleophilic orbital. It's the non-bonding orbital on oxygen for this carboxylic acid that has resonance with the carbonyl. And over here, it's the non-bonding orbital on nitrogen that has resonance. And so can I use an orbital interaction diagram to explain which of these two carbonyls will be easier to add some nucleophile to? Maybe you're doing hydrolysis with a hydroxide anion of esters versus amides. Can a diagram like these MO diagrams explain things? So I'm going to draw two diagrams side by side. And in one diagram, I've got an oxygen lone pair that is adding. I've got an oxygen lone pair that's adding to a carbonyl. And I'm going to look at this gap here. There's a gap between the filled and the unfilled orbital. I'm going to pay big time attention to that gap. Now, what happens when I go from a non-bonding orbital on oxygen to a non-bonding orbital on nitrogen? Well, nitrogen is less electronegative. That lone pair on nitrogen, the non-bonding lone pair, should be higher in energy. And what that means, because it's higher in energy and the CO is in the same place, pi star CO, this gap is going to be smaller. Look at that gap. Smaller. How much smaller? I don't know, but I'm being qualitative. These diagrams are qualitative. And if you get a smaller gap, you'll get bigger interaction energy out of this. So let me go ahead and draw my new orbital down here. I'll draw that new orbital. Here's my new orbital. It's a pi-like orbital. It'll have pi symmetry associated with it. In this case, it would be pi NCO. And then I'll also get a new pi, and there will be big time interaction energy because my gap was small. So that's big IE. How big? Well, I don't know, but bigger than what I got over here. Smaller IE. Right? That's all I know is one One interaction energy for oxygen is smaller, and the interaction energy I get out for the nitrogen resonance is bigger. And so I'll end up with this new pi-like orbital with electrons in it. And I don't really care about that, because if I'm trying to figure out the reactivity and ability to add, so if I lower the energy of this orbital over here by a certain amount, by interaction energy, I have to create a new orbital that's higher by that same amount. And that's the orbital that I'm interested in. I'm interested in this new pi star orbital that has resonance between nitrogen, carbon, and oxygen. And you can see immediately, right, because I started at the same level here with my same pi star, the nitrogen will create a new orbital that's harder to add to. The answer to this question is that it is easier to add to the ester, and it is harder to add to the amide. It's harder to add to this higher energy orbital. So it's, right, harder to add to that new pi star orbital, harder to add. It's higher in energy. It's harder to add to higher energy orbitals that are empty. You know, it's just harder. And that comes out of this diagram. Why does resonance make carbonyls less reactive? So notice how all I changed here was one thing, oxygen to nitrogen. I left everything else the same, but you can end up with some powerful predictions sometimes that aren't so obvious. All right, so you know that equation, on the top of that equation, the numerator is orbital overlap. And I want to take a look at the implications of orbital overlap. They have big time implications. Let's step away from these interaction energy diagrams and go a little bit deeper on this idea of orbital overlap. So in most cases where we talk about overlap, we have two orbitals interacting in energy. So I've got maybe some two s orbitals on hydrogen interacting to make a sigma bond between two hydrogen atoms, or maybe I have two p orbitals overlapping in space to make a pi bond. There's electron density above and below the plane that's got pi-like symmetry. Or maybe I interact an sp3 orbital with some empty orbital on hydrogen, make a bond between carbon and hydrogen or something like that. Now there's always two arbitrary phasing combinations. If I have like phasing, I make a bond. If I have unlike phasing, I'll generate a new antibonding orbital. So these are cases here where, because I've matched the phasing, so I've got green and green, I've got green and green, and gray, I've got green and green. That means we will have a productive bonding combination here that is favorable, that makes a new bond. So if I have one electron in each orbital, I'll generate a new bonding type orbital. And then I'll also generate a new orbital that's higher in energy by the same amount. That's a star type orbital. So I guess these are all cases, they're not all, I'll take the sigma cases here. I'll end up with a new sigma orbital and a new sigma star orbital. There's a non-zero interaction energy when you have orbitals of like phasing overlapping in space. You know, you don't always have to draw out these diagrams. Sometimes you can create simple rules that allow you to avoid drawing diagrams or working with equations like overlap divided by gap. And let me show you a simple rule that is a direct consequence of this concept of orbital overlap. And this rule is called Brett's rule. And Brett's rule is simply formulated as saying, bridgehead olefins are unstable. Don't make bridgehead olefins. Now you don't know what a bridgehead is, so let me explain that. When you've got bicyclic systems, like this one over here, this is a bicyclic system composed of normal sized rings, like 5, 6-membered rings, sometimes 7 you would include in there. And in this case, the two atoms that join those ring systems are called the bridgeheads. So let me go ahead and label that here. This atom with the red dot is one bridgehead. That's the other bridgehead. Those are the bridgehead atoms. In this case, they're bridgehead carbon atoms. And if you try to make a double bond to one of those bridgehead atoms, it's not going to be stable. Well, why is that? The reason is, if you draw out the geometry, if you could see this in space in 3 dimensions, you'd end up with this orbital. You'd end up with one of these orbitals going up and down. Right? One orbital would be sticking up and down. That's for this one right here. I'll just go ahead and phase that in. And the other orbital, unfortunately, because of the orientation of that bridgehead, will be sticking kind of out at you and then behind this carbon atom. So I don't know how to phase that. These orbitals are orthogonal when they're at the bridgehead. you cannot interact those two p orbitals, right? It's the same, the two p orbitals might start off with the same energy, but this is a case where you would end up with no interaction. There's no overlap between those, no net overlap between those two. And there would be zero interaction energy. If there's no overlap, the interaction energy is zero. And so you wouldn't really end up with two new orbitals. You would just end up with electrons that are still just single unpaired electrons. This bridgehead olefin, if you drew it like that, would actually behave as a diradical. It would just behave as a radical. It would react with molecular oxygen. Every single collision would lead to a successful bond. It would be completely unstable, wouldn't have any pi character to it. So you have to have good overlap in order to make bonds. And if you don't have effective overlap, if orbitals are orthogonal to each other or 90 degrees, they can't have good overlap. Okay, let's take another look at the implications of orbital overlap. Right? Let me show you a simple example here. We're simply going to take this substrate that is rather symmetrical. I've got this system here that has two pi systems. Right? Here's a double bond, here's a triple bond, and there's pentyl groups on each end. Everything else is the same. So really, if we take an epoxidizing reagent, I don't know if you remember MCPBA makes epoxides with pi bonds. If you react that with this system, what's the product going to be? And orbital overlap answers this question for you. So it turns out that the product of this reaction is going to be that you make the epoxide out of the double bond. Well, why is that? It's not so obvious why that should be the case. If I draw out all the atoms on this alkene, it's got more stuff on there. It's more hindered. Right? That alkene is more hindered because of those H's. You'd think that the more hindered pi system would react slower. There's more double bonds over here in this triple bond. Two double bonds. There's two pi bonds. And it's radially symmetrical, meaning that you can approach from more trajectories. So this one over here only has one pi bond. Why do you react with the single pi bond that's more hindered instead of the less hindered triple bond that has two pi systems? That's not so obvious, but let me just remind you of something. And this is something that any crystallographer could tell you. And that is that CC triple bonds are shorter. Look at the distances here for a CC triple bond. It's 1.2 angstroms for a CC triple bond and 1.46 angstroms for a typical CC double bond. And those bond distances are amazingly consistent. The implication of that shorter CC triple bond is that you will end up with more effective overlap in the case of the CC triple bond. So if we draw that out, if you have more effective orbital overlap between these p orbitals, you're going to end up with a more stable pi bond. Which sounds great, doesn't it? More stable pi bond. Over here, boy, they're kind of far away. It's kind of hard for them to overlap. And you just won't end up with as stable a pi bond for a double bond. The pi bonds of CC triple bonds are more stable. And you'd think that would be great, but we're not interested in stability. We're interested in reactivity. And because the pi-like orbitals in the triple bond are more stable, that means they are less reactive. So, right, there's this whole sequence of consequences here. So because those atoms are closer together, you get better overlap. And because you get better overlap, you end up with a more stable pi bond, more stable pi. But more stable is not good for reactivity because that means less reactive. Lower energy pi-like orbital means less reactive pi as a nucleophile. We're not talking about pi star, we're talking about pi. Less reactive pi. So the pi electrons of the triple bond are less reactive. So even though it's less hindered, even though there's two of them, right, we're not interested in factors of two here. We're interested in big time factors. Double bonds are more nucleophilic, just based on orbital overlap is what would predict that. Okay, let me go a little bit more into this idea that overlap is important. Having two orbitals, as you come closer with two reactants colliding together, or if you're trying to have resonance of some kind, orbital overlap is super important. It's all in this equation right here. Overlap is the numerator to this equation that tells us how much interaction we get by interacting two orbitals. So let's go ahead and take a look at this hypothetical reaction where chloromethane is just floating around in solution and these two molecules collide with each other. Is it reasonable to have this carbon-chlorine bond attack this carbon-chlorine? I mean, that doesn't look reasonable to me. If I draw out the product for the reaction, the product is going to be another chloromethane molecule. Now, unfortunately, when I do that, I'm going to end up with this primary carbocation. That's not even primary, it's worse than primary, and a chloride anion. Now, that's not good, and it has nothing to do with the products. It's because we're taking the worst kind of orbital, this orbital down here that's low in energy, and we're interacting it with the worst kind of antibonding orbital. The gap there is huge. You don't expect much interaction energy, right? If you're taking the worst kind of nucleophile and the worst kind of electrophilic orbital and interacting them with each other. You get very poor interaction there. But we see this interaction occurring all the time. There's a different type of reaction that you learn about as one of the first reactions when you take an introductory course in organic chemistry, and that is an SN1 reaction. In an SN1, step one is ionization, typically of carbon-halogen bonds. We see these all the time. And this is the same two orbitals interacting, sigma of a carbon-chlorine bond interacting with sigma star of a carbon-chlorine bond. Now I can't draw both of these orbitals. I can't draw the sigma and the sigma star without ending up with a mess. So I'm going to draw it on two different pictures, and you have to merge these two pictures in your mind. So if I draw out a picture of a sigma-like orbital for a carbon-chlorine bond, it would look something like this. I would end up with electron density between the two atoms, between the carbon and the chlorine. That's what a sigma orbital typically looks like. And the orbitals stick out on the opposite ends a little bit. But there should be electron density between the two. And it should be aligned, the orbital should be aligned around that axis between the carbon and the chlorine. But what about the antibonding orbital? This is where you would attack. If you try to add over here to an antibonding orbital, the antibonding orbital is mostly centered in the back. There's not electron density directly in between. Let me go ahead and draw out a picture of a typical antibonding orbital. If you could look at that, it's biggest in the back. That's where you attack when you do SN2 reactions. And then if I phase this, I'll arbitrarily phase it so it's phased hashed. And then I'll have these two tiny little orbitals in between. This one would be hashed a little bit. And then on the back end, I would have this other, whoops, I've got that, the hashing is wrong. The hashing should be, yeah, that was correct. Sorry, that was correct. And so I'll end up with this orbital phasing diagram over here. It's biggest on the ends. There's no electron density in the middle. So I'll just write no electron density, right? If you put electrons in there, you wouldn't have any, antibonding orbitals are typically empty. But if you put electron density in, or electrons in there, they would not spend any time directly between the carbon and the chlorine. Now, these two orbitals exist and they coincide in space. So in your mind, I'd like you to try to merge these two pictures together. And what you would see is that the orbitals which are aligned along the axis actually overlap in space 100% of the time. The sigma and the sigma star overlap 100% of the time. And because overlap is more effective here, right, then probably maybe we should draw SN1 arrow pushing like this. The sigma bond attacks sigma star and you break the bond. Maybe that's the way we should have drawn that arrow. That's exactly what's happening in an SN1 reaction. It's the sigma bond that is attacking sigma star. And because overlap is so effective, I hate to use a red pen here again, right? If you've got lots of good overlap, you get big time interactions. So this is the case over here. We have good overlap. If you have good overlap, then you can end up with effective reactions. So overlap is critical. Just having them collide in, randomly in space, you're not going to get that excellent overlap. All right, let's switch away from this overlap concept and talk about, well, this is kind of related to overlap, a simple, powerful description of nucleophilicity and electrophilicity that is based on something simple, and that is bond length. And let me just start off by saying something pretty easy to understand, and that is that longer bonds are weaker. Longer bonds are weaker. That is such a powerful statement. Longer bonds are weaker. The implication of that is this. Let's go ahead and take a look at some hydrido reagents that you would have seen in an introductory organic chemistry class. So hopefully you would have seen reagents like borohydride, called hydridoborate, attacking things, carbonyls usually, almost always, exclusively. You've seen borohydride attack carbonyl groups. You've also seen lithium aluminum hydride attack carbonyl groups. And they're not equally reactive. And I could have predicted that based on bond length. So when you drop to lower rows in the periodic table from boron to aluminum to, what's below aluminum? Gallium or something, right? What happens is as the bonds get longer, they get weaker. So the bonds are weaker. Let me go ahead and depict that. If I have a new orbital here, a new bonding orbital for this hydridoaluminate bond, sigma, aluminum, H, aluminum minus H. I don't know how to fit that minus in there, right? That bond is weaker. That's how you would depict that. And there's this thing that happens when you make weaker bonds, is that you have a higher energy bonding orbital, but you also have a lower energy antibonding orbital. The bond is weaker. It's easier to break. That should be obvious. The bond is weaker. And if I kept going in the periodic table down to further rows, down to gallium and whatever's below gallium, I'll keep seeing this pinching effect of the filled and the unfilled orbitals, the filled and the unfilled, whether it's pi, whether it's sigma star and sigma, pi and pi star, you get this pinching effect as you go to longer bonds. So the prediction from this is that the tetrahydridoaluminate should be more nucleophilic than hydridoborate because the bond is longer. And all we needed to know was bond length. You just needed to recognize that aluminum is below boron in the periodic table and will have a longer bond. And so the important implication is hydridoborate is more nucleophilic. How much more nucleophilic? Way more nucleophilic. Boy, lithium aluminum hydride is way more nucleophilic. It reduces esters, amides, any kind of functional group. And that's just a consequence of the bond length. So remember this effect of bond length because you just need to look at a periodic table. Okay, so that's talking about nucleophilicity. Does bond length tell us something about electrophilicity? Absolutely it does. If you go to the halogen row or halogen column, fluoride, chloride, bromide, iodide, right? If you look in that column of the periodic table, as you walk through that sequence, you're getting to longer and longer bonds. And so what happens as we go to longer and longer bonds? Well, the bonds are weaker. Now, I don't plan to do a whole lot of nucleophilic attack, maybe in an SN1 reaction with these bonds, but if I did, what I would find is that those bonds become more and more nucleophilic. They're weak. The electrons are ready to do something else. But at the same time that we're raising the energy of that sigma-like bonding orbital, right, these are all the sigma bonding orbitals, I'm also lowering the energy of sigma star. As we get to longer and longer bonds, they're easier to break. I'm not sure I did a good job drawing that. Let me draw this a little lower. There's this pinching effect. So as these new sigma star orbitals should be lower in energy. This is why it is easier to do SN2. So it's faster to do displacement here. That's fastest because sigma star is lowest in energy. You know, I don't know what you were taught when you took an introductory organic chemistry course. They taught you something about leaving group ability or made up some kind of nonsense about it. That has nothing to do. It's the sigma star orbital that determines how easy it is to do an SN2 displacement. Alkyl iodides are more reactive because sigma star is lower in energy. It's not the electronegativity is not what's going on here. It's just the sigma star orbital. And if you just knew this effect of bond length, you could have predicted that without creating any additional ideas about leaving group ability or something like that. Longer bonds are weaker. They're easier to break. They're more nucleophilic. Simple idea. Okay, let's switch from bond length. Let's stick within the second row of the periodic table, carbon, nitrogen, oxygen. So I want to compare the effect of conjugation, resonance and conjugation, versus systems that aren't conjugated. Here's two molecules, two isomeric molecules, so pentadiene molecules. One of them has conjugation between the two double bonds. The other pentadiene has no conjugation. There's a CH2 group in this right-handed pentadiene that prevents conjugation between those two double bonds. So which one is more reactive as a nucleophile? Right? If I come down over here and I think about this this reaction with some sort of an electrophile. It could be a carbocation, could be Br2, could be MCPBA, right? So in those cases, right, if I use this pi system as a nucleophile, I'm going to end up with a carbocation in the product, as I've drawn over here. So, I mean, if you're adding a carbocation, if R plus is just a simple carbocation, I'll end up with this carbocation here in the product. And it'll be a similar situation over here if you use the unconjugated, the non-conjugated pentadiene molecule. Now, which one of these should be faster? Well, I think we know which one should be faster. The one over here should be faster. Why is that? If you took an introductory course in organic chemistry, they would have told you, oh, that's because the product is more stable. You know, half the time in organic chemistry, more stable products form faster. The other half the time, less stable products form faster. So you've got to be super cautious about applying that rule. So it's slower. It is the unconjugated systems are less reactive. It is not the product stability that determines why the conjugated system is more nucleophilic, right? This is more nucleophilic before any reaction occurred. We'll see that in just a second. It's not because the product is more stable, it's because conjugated dienes are more nucleophilic. And if we look at dienes acting as electrophiles, suppose you added some nucleophile to the diene, like this. We'll talk about this a little bit later, but in some cases you can add anions, carbanions to dienes. That's how they make synthetic rubber, through anionic polymerization of dienes. And so if you look at the product, you see that the product for addition to the conjugated diene is a resonance stabilized allyl whereas if you add to the non-conjugated alkene, you get just a plain carbanion that's not stabilized by resonance. And if you use thinking from sophomore organic chemistry, you would say, oh, you know, this should be faster because the product is more stable. But that's not why it's faster. It's faster because the diene, the conjugated diene, is more electrophilic. Not because the product is more stable, but because the starting material is more electrophilic. It's easier to add to them. Let's go ahead and depict that, because there's a simple rule we can apply here that extends way beyond this simple pair of molecules. And that rule is that when you have conjugation, it's kind of like the bond length effect. When you go from a simple alkene that has no conjugation to a diene, what happens is the HOMO gets higher in energy, and the LUMO gets lower in energy. Conjugation makes pi systems more nucleophilic and more electrophilic. And as you keep conjugating, adding more and more conjugation with benzene rings, with double bonds, with triple bonds, as long as the overlap is good, you're going to see this pinching effect of the HOMO and the LUMO, of the pi and the pi star. Right? They're more reactive. Conjugated pi systems are more reactive nucleophiles and more reactive electrophiles. And if you took this to the nth degree and decided to make a polymer out of acetylene, that polymer would just be this infinitely long die, not infinitely long. Your prediction would be that these orbitals would get so close in energy that they would all be mixed together. In fact, this concept is well understood. You can make something that's the equivalent of a molecular wire by having these long, long chains of conjugation where the filled and the unfilled orbitals are mixing with each other. So we're not interested in molecular electronics in this course. We're just interested in, you know, should we start our arrow with an unconjugated unconjugated pi system or a conjugated pi system? Start your arrows with the conjugated one. Those should be more reactive. That should increase the reactivity of that system. Okay, so those are the orbital trends that you need to understand. You need to know the relative energies. So we started off by talking about the effects of hybridization. Keep that in mind. We're going to come back to these effects of hybridization. More p character means more nucleophilic. So if you're a pair of electrons in an orbital with more p character, you're going to be a more nucleophilic pair of electrons. I told you you have to memorize the relative energies of these canonical filled and unfilled molecular orbitals. So the relative energies tell you a lot about where you ought to be starting your arrows. You know, if you don't know anything other than this, you're in pretty good shape for a lot of the arrow pushing that we do. You need to know the effect of electronegativity. When I replace carbon with a more electronegative atom and I keep making it more electronegative, all the orbitals associated with that atom should drop in energy. If I were a pair of electrons, I'd want to be near a nucleus that has more protons in it. That's electronegativity. Makes sense. And it's true whether you're talking about just a lone pair orbital centered on one atom or a bond. If I replace one of the atoms in this bond with a more electronegative atom, all the orbitals drop in energy. Sigma drops in energy, sigma star drops in energy. All the orbitals associated with that carbon X bond will drop in energy. Other bonds far from the molecule, that's not the effect. But here, the orbital that's associated with that, the carbon-carbon, carbon-nitrogen, carbon-oxygen, right? The bond should be less nucleophilic, and it should be easier to do SN2 as you go to carbon-fluorine. That's the prediction. You need to understand the effect of bond length. Longer bonds, like a double bond, is longer than a triple bond, CC triple bond. So CC double bond should be more nucleophilic. It should also be easier to add to. If you look at the effect of bond length on halogens, carbon-halogen bonds, so it's easier to do SN2 on alkyl iodides because sigma star is lower in energy. Right? Longer bonds are weaker. That hybridization effect applies to bonds, like over here, not just individual atoms in hybrid atomic orbitals. And that conjugation effect also applies to conjugation. This pinching effect. This conjugation predicts that the more conjugation you have, the more nucleophilic and the more electrophilic those orbitals will be. So as we go through this class, we're going to be doing a lot of arrow pushing, and these powerful rules that just, if you know the periodic table and some simple ideas about the energies of canonical orbitals, you can make powerful predictions about where to make your curved arrows start and where to make your curved arrows end.